That works.
Okay, cool. Yes, today I'll talk about efficient image to 3D asset generation. When people hear you're working on image to 3D, the first question is usually, how good does it look like? But today, I want to focus on a slightly different question. How fast can we make it useful? Because in real application, latency is more than just a benchmark number. It changes the entire user experiences. If generation takes an hour, it's an offline tool. And if it takes 1 minute, it is a waiting user experience. And if it takes a few seconds, it starts to become interactive. So this talk is partly about 3D generation and partly about my personal impatience with the progress bar. So 3D generation is becoming relevant to many areas: interactive creation, XR, and robotic simulations and game assets, and more recently, agentic world creation. So across all these applications, users do not sense the model inference time directly. They care about the end-to-end latency. From the moment they express an intent, click submit, and the moment they see an output that actually actually can work and can iterate on. So if every iteration takes several minutes, the artists are not really creating interactively, they are mostly waiting politely. For robotics, the slow asset generation limits the diversity of simulation. And for games, one asset is never enough. You usually need hundreds of thousands of them to create a game world. And for agentic world creation, latency becomes even more important. Because the generation may sit inside a loop, generate, inspect, simulate, edit, and regenerate. But in 3D generation, runtime is ambiguous unless we specify the output. So a 2D image is mostly a grid of pixels, and a 3D asset is much more structured than a grid of voxels. So taking a common file format, GLTF, for example, it has geometry, topology, mesh connectivity, UV maps, the texture atlases, materials, etc. This is why image to 3D is not just another image generation problem with 3 dimensions. It's a pretty render that can hide many problems. Like the mesh itself can have holes, the topology may be unusable, and the faces may be intersect, and the UVs may overlap. The asset may look great in one view and completely fail when importing to the engine. So a pretty 3D render is not necessarily a usable 3D asset. So what would be a useful 3D asset? A good start is Unity or Unreal can open it without any complaining. So it needs a clean mesh, reasonable poly count, a clean UV atlas with proper island without so many fractures, and nice textures and PBR materials to support realistic appearance, and correct scale and pivot, and potentially with separate parts and hierarchy for animation and editing, and collision or physics proxy and the export compatibility. So this matters because the downstream users do not consume screenshots. Game engines and simulators consume the complete structure assets. So in this presentation, I will talk more than just faster neural network inference, but also many tiny but necessary operations that makes a generated asset actually survive contact with an engine. So how do we reduce the latency at each phase? So we have the generative model parts and the rest deterministic operations in the system pipeline, like mesh extraction, simplification, UV unwrapping, and texture baking, and the texture completion, export, and validation. So at a high level, I group the model level acceleration strategies into 3 axes. First is to skip the test time optimization, move from per asset optimization to feed forward generation. And second, use fewer generation steps. This includes distillation, one step or few step generation, rectify flow, and CFG distillation. Third is to make each step cheaper. For example, sparse attention, token pruning, quantization, and adaptive decoding. Then separately, we have system-level acceleration, overlapping the CPU, GPU, I/O, and the post-processing works. So let's start with the model-level acceleration first. I'll first focus on one basic problem, how the choice of the representation and the generative process changes the latency. That is, can we change what the model predicts, and so there is less work to do at the inference time? So early text-to-3D systems, such as the Dream Fusion, are powerful, but they rely on a test time optimization. For each prompt, you optimize a 3D representation using a gradients from the 2D diffusion model. That gives high flexibility, but is slow, and often it's an order of hours slow. And later systems, such as Instance 3D, move towards feed-forward generation. Instead of optimizing a set from scratch at every time, the model predicts multi-view images and reconstructs the 3D more directly. This changes the latency from hours range to seconds. This is a great progress. It do not solve a new optimization problem every asset, but amortize the work into the training. Still, in the above work, they choose NeRF or Gaussian splatting as a representation for learning. This makes sense. They are differentiable and also continuous fields, and their structures are very suitable for as a learning target. But also they are very good for photorealistic renderings. But for the assets, we often still need an explicit surface. That means at some point we need to extract a mesh from these implicit representations, and this conversion is not free. It takes a solid amount of time. It can introduce noisy geometry and holes and the high triangle counts or topology that is sometimes difficult to edit. So one efficiency question is, can we migrate to other representations that are easy to learn and also closer to a usable engine-ready asset? The answer is yes. One direction is to become 3D native. Instead of generating only views and then reconstructing later, the models can generate latent 3D structures directly. For example, a 3D shape-to-vec set works with sampling the shape latents and decoding into a signed distance field. And Clay further pushes this direction by combining the geometry generation stage followed with a control net style multi-view image generation network to create the textures and materials for the mesh. This approach reduces amount of per instance optimization and better align with the model output with the final asset. But still, there is a gap. SDF and implicit fields are good for shape generation, but they often require mesh extraction and post-processing. And I have to say, not all the meshes are equally useful. Here is a simple example. The marching cubes can extract a surface from the SDF, but the resulting mesh often have many triangles and does not follow the semantic structure. On the right side, we have an artist-like mesh. It has fewer faces, cleaner edges, and the structure that corresponds to meaningful parts of the object. This matters because the downstream tasks care about the polygon quality. If this toaster mesh has a million tiny triangles, it may render, but it's not very pleasant to edit, rig, simulate, and compress.
It's not from this room.
Okay.
Hurry.
Okay, we shall continue. Yes. Also, naturally, we have an idea about improving the efficiency. So directly producing a representation that avoids extensive cleanup. And this idea leads us into the direction to generate mesh topology directly. Mesh GPT and Mesh Anything show the mesh sequences can be modeled with autoregressive nest token prediction, which require discretizing vertex coordinates. The inference codes scale quadratically with the mesh size, and our recent work, Mesh Flow, pushes it further by introducing a variational autoencoder that represents both continuous vertex positions and discrete connectivity in a continuous latent space. which is significantly more compact than the prior token-based mesh representation. Based on this, we built a 3D generator with rectify flow, which generates all mesh vertices and edges in parallel. This pushes the latency to be 18 times faster than the fastest autoregressive generation, reaching around 1.2 seconds, while also achieving the state-of-the-art accuracy across a mesh generation matrix. This is exciting because it attacks a problem at the representation level. And if the model directly outputs a clean mesh, we can reduce or even avoid expensive extraction and simplification steps. And that leads to the next missing piece, texture and UV structure. So a mesh alone is not a full asset. In production, many of the visual details come from the textures and maps. Like normal maps can encode high-frequency geometry details without increasing the mesh complexity. In the left image, you can see a flat plane plus the normal map in the middle can display a vivid geometry displacement rendering on the right. And the UV maps define how the 2D textures are placed onto the 3D surfaces. So besides the geometry generation, there is also a large amount of work in the post-processing steps, like UV unwrappings, normal bakings, and texture completion can become the bottlenecks. A promising direction is to generate meshes with native UV segmentation. The idea is that instead of first generating geometry and then asking another algorithm to unwrap it, the model can learn surface structure and UV islands as part of the generation. So there's a recent paper, strips as tokens, represents a mesh as connected strips. So the generation order follows a natural flow, artist-like edge flow of the surface. So this gives the model a better inductive bias for learning the clean topology and also artist-like the flow for surfaces. The more importantly, it can also insert the UV island boundary tokens into the sequence. So the model generates geometry in the meantime and also learn how the surfaces should be partitioned for the UV unwrapping. This is very important because the UV unwrapping is not just a mechanical step. It also reflects the semantic and geometry decomposition. If the model understands the object parts, it may also learn a better segmentation for texturing. And the output of the strip as tokens with a simple post-processing can become the final UV coordinates and texture atlas. This work opens up broader trend, like how to fold the post-processing decisions into the model's output itself. And so far, we discussed what the model predicts. The second major axis is to reducing the number of generation steps. A very practical approach is distillation. The basic idea is to start from a strong multi-step teacher model and train a student model to approximate the same generation trajectory using fewer sampling steps, like progressive distillation, CFG distillation, and the other latent consistency models are representative examples for this direction. So the advantage is that it can often be applied to an existing checkpoint, so it's relatively fast to get it working. And the downside is that the student is limited by the teacher and the quality can degrade if the distillation is too aggressive. In practice, we can happily say that it can give 10 to 25 times acceleration. Well, it's huge, but you're not free. The failure mode is often over-smoothing or loss of fine-grained details if not doing carefully. Another alternative is to train the model for fewer steps or one-step generation from the beginning. Like methods like the rectify flow and the mean flow try to make the generation path easier to sample, so the model does not need dozens of denoising steps. The advantage of this model is like it's self-contained and does not necessarily require a teacher. And the downside is that you typically need the full training, which is very expensive. But the latency potential is very attractive. With one-step generation, sub-second or near one-step generation becomes possible. So the third axis is to make each step cheaper. Here, I want to mention two papers from Tencent Hunyuan Group, Elastic Diffusion Transformer and Flash VDN. Elastic Diffusion Transformer noticed that the generative process of DIT is highly sparse. While this sparsity varies significantly across samples, So it equips each DIT block with a lightweight rotor that dynamically identifies the sparsity from the input latent, and it determines whether the corresponding block can be skipped. This saves 2 times inference cost. And Flash VDM accelerates the pipeline in more standard ways, in 2 ways. First, it applies many engineering optimizations, like torch compile to reduce the framework overhead, FP8 quantization lower the memories, and compute the cost where the model is less sensitive, and flash attention improves the attention latent efficiency. And another insight is about 3D is decoding. A dense SDF decoder wastes computation by querying the entire volume, even though only the surface near regions are actually matters for the mesh extraction. So hierarchical decoding can turn this into an octree-like coarse to fine process. So decode the coarse area only and identify the likely surface regions and refine only these regions. Another thing is adaptive KB selection to further reduce the decoder attention cost. So instead of every spatial query attending to all latent tokens, each local subvolume can select only the most relevant KB tokens. And together, this engineering and decoding optimization gives roughly 4 to 5 times end-to-end acceleration, while preserving the core vecset generation quality. And now I want to move from model level acceleration to system level acceleration. A common mistake is to only measure the neural network inference time, while for an actual 3D asset pipeline, inference is only one part. The full request, including the processing export, file upload, and sometimes engine-specific checks. So aside from the diffusion model, we still have leave a lot of latency on the table. Usually after the mesh finish generation and texture is created, we usually need like the mesh extraction, simplification, and UV unwrapping, texture baking, texture completion, and export validation. So each stage has its own failure modes. Simplification can remove details, and the UV unwrapping can be extremely slow on the complex geometry. And texture baking needs multi-view consistency and the super sampling for anti-aliasing, which requires more pixels. Yeah, and texture completion must be a 3D aware and sometimes may require another generation model. Export validation can reveal issues that were invisible in the render preview and need to be fixed. So for the practical efficiency, we're also faced with the quality and the speed trade-off that we need to properly choose the poly count and resolution budget based on the downstream functionality and optimize the whole pipeline by choosing the faster rasterization methods or the GPU accelerated operations and run everything as parallel as possible without cracking the memory bound. So one system-like trick is intra-request parallelization. Within a single request, different resources can work at the same time. While the GPU runs in diffusion, CPU workers can prepare back projection data, the KD tree to model the 3D geometric neighborhood, and the mesh metadata or export structure. And I/O can also be overlapped with a compute. The principle is very simple. Do not let the GPU wait for the CPU, and do not let the CPU wait for the GPU unless absolute necessary. And for the 3D generation, such system-level engineering is especially valuable because the pipeline naturally contains so many heterogeneous workloads and needs to store a large capacity, dense information across the different devices. The next level is a request level overlap. While we talk about efficiency, we should also care about the scheduling, resource utilization, and robustness under real user traffic. In a serving system, while request one in GPU is doing the prediction, request 2 can be running in pre-processing, and request 0 can be in post-processing. So across the requests, the GPU prediction is running in sync, while the pre and post-processing can run in async. For the production deployment, this can reduce the idle time and maximizes the service throughput. So putting all these ideas together, we can reach an end-to-end latency about 8 seconds. Let's see. Yeah. Here shows a demo we built on the H100 GPU. And you can see the timer there is a work log time from clicking the generation to get the asset that can use. Here I upload an image of the Denver's Liberty Bell. It first run the foreground segmentation and then our entire mesh generation, geometry processing like UV unwrapping, normal baking, texture gen, and eventually export into a GLB file ready to be downloaded and dragged into the Unity or Unreal Engine. So as you can see, with the 8 seconds, we're not fully real time yet, but we're entering the range where the iteration process can become truly interactive and practical. This one shows some of the qualitative results from our asset gen. It will be a faster turnaround of many assets we generated. As you can see, with a tens of seconds budget, the output still looks good, and even the input condition is just a frontal or near frontal image. It's able to guess the whole shape, even the back wheels, in a pretty good manner, and looks pretty robust among a wide range of the contents in these categories. Okay. So let's speculate a little. If we keep this multi-stage pipeline, a plausible target might be around 4.5 seconds, like 2 seconds for topology-ready mesh generation and 1 second for parallel UV unwrapping, and about 1.5 seconds for the 2K texture generation. And a more aggressive direction is one-stage asset generation, like generate a asset latent, then decode mesh topology, UVs, and texture atlas together. In that scenario, the theoretical latency could be close to 2 seconds. So far, not all such all-in-one network doesn't exist yet, where all the numbers are all speculated from the end format needed for the engine-ready asset. And I hope everyone in the room and the community can keep thinking on where this field might go, like fewer hands-off points and fold more process into a model output, and the more native asset structure and more overlap between the geometry and appearance. The next question is for everyone. So when generation reaches a second level latency, the 3D asset can be created at almost the speed of thought. The game asset generation is no longer need to be an offline editor workflow. It can happen at runtime. Imagine a player saying that, I want a sword with a sapphire on it, and in 1 second later, they can hold it, inspect it, and use it in the engine. This also opens up a much larger playground for the agentic 3D creation. With faster generation, agents can operate in a closed loop. They generate, simulate, evaluate, modify, and regenerate in a really fast way. So more broadly, the faster asset generation can become a new UI primitive for interacting with the 3D. From video or image observations, a system could continuously convert what it sees into the assets, maintaining an interactable, render-friendly world state with an explicit asset graph. This means like interactive AI assistants can be for everyone, and the long-tail training environments for the embodied AI are much easier to create. This is a future I'm pretty excited about. So I also want to highlight several related works from our group, including the mesh region to refine the mesh and work gen and mesh flow at this conference. You're super welcome to check out these works and talk to our amazing team members. And so great thanks to the teammates and collaborators. Building such a complex pipeline requires modeling, system optimization, data preparation, product feedback, and metric design, and many rounds of debugging. So thank you. And I'm happy to take questions during the break time.